Hello viewers, welcome to my channel IITJ Olympiads and AP Physics with Ambarish. And today I have brought a very exciting challenge for all of you. It's an original challenge created by me, and I felt very happy after creating this challenge, and I'm going to share this with you, and I'll also be presenting solution later on, and see if you want to try this out on your own, and then you can have a look at my analysis later on. So here is the challenge. Okay, I'll explain to you the problem statement. A massless and frictionless thread is tied to two pegs and a small frictionless bead is strung onto it. So this is a peg A and this is the peg B, and then there is a thread, and the thread is massless and frictionless. Okay, and then there is a small bead. I've drawn it like a pendant, but it is supposed to be, imagine it to be a very small bead and with a hole inside, and so that it can slide without friction, and it's a very small bead, and you can ignore the moment of inertia and all effects, so you can assume that this is in pure translation kind of. Okay, so small frictionless bead is strung on it. Now from equilibrium position, the bead is given a small kick parallel to the xz plane. So what is the xz plane? This is your x-axis, vertical is the y-axis, and z-axis is coming out of the page, or you can think of it as going into the page. Okay, of course, if x cross y is coming out of the page, so z-axis, I hope you got it. Okay, so I've given it a small kick in the xz plane. So what will happen? It will start oscillating, and or whatever motion, if you want to call it an oscillation. So it is, what is given is that it traces a path parallel to the xz plane as shown in the figure. So in the top view, if you see from here, it will have some motion in the xz plane. So suppose you have given it a kick in this direction. So what is happening? It is tracing a path. What kind of path? It is going like this, and then it is coming like this, and it is going like this, and it's moving along this path. See, and it's going like this. Okay, and then it is coming back to the same place. Okay, so obviously it's a periodic motion, because finally you see it's a closed path. From wherever it starts, it gets finally closes onto itself. Okay, so it's a closed path, and it's obviously a periodic motion. Okay, and for this periodic motion to be possible, there will be a certain ratio of d to l. Suppose this distance is d, and the total length of the string is l. So there will be a particular ratio of d by l for which this will be possible, and we have to calculate that ratio. Okay, and the assumption is that the kick is very small, the bead can slide without friction, and the kick is in the xz plane, and it's a slight kick. So this figure is highly exaggerated. You can imagine it to be maybe 100 times exaggerated, or maybe 1000 times exaggerated figure. We are interested in only very small oscillations, and thread is absolutely massless and frictionless, negligible radius of the thread. I mean, it has a finite length, but the mass is negligible, and the bead also has got some mass, but its size is very small. So you can treat it like a point bead. Okay, but it can slide without friction. Okay, so if you want, you can try out this challenge on your own for some time and see if you can figure out the key ideas behind this problem, and I'm going to get into the analysis immediately. So let's see what's happening here. Okay, so let me start the analysis. So if you are trying it out, please pause the video. This is your time. Okay, because otherwise it will be a spoiler immediately. Okay, so let me start analysis. So if you see, there are two types of oscillations happening for this bead. Suppose the kick was along x-axis, then you know that since the distance of the bead from A and B, the sum of these two distances is constant. That means what? The locus of this bead is going to be an ellipse. So therefore in the xy plane, the oscillations are going to happen. If we ignore the z direction, then the oscillations are going to happen along the arc of an ellipse. Okay, so I can find out the time period in the xy plane. So before getting into the exact solution, I'm just telling you the approach, how I'm going to approach this problem. So I can find out the time period in the xy plane in terms of d and l. If I know the radius of curvature of the ellipse, then I'll show you the mathematics. But in essence, once I know the radius of curvature, I can find out the time period as 2 pi under root r by g. Okay. Another thing is, suppose I had the kick had no component in the x direction. It was a pure kick in the let's say z direction. In that case, the pendulum will be just coming out of the page and going into the page, and it will be oscillating with this AB being the instantaneous axis of rotation, and it will be like a simple pendulum. And if this distance is b, then it will be a pendulum of length b, and 2 pi root b by g is going to be its time period. And obviously since it's forming a closed path, that means what, the two time periods have a well defined LCM. The presence of a closed path means that LCM exists, otherwise it will not be a periodic function. So there is x time period and there is y time period, and when you get the time period, the LCM of the two time periods, that will be the time when the particle will be again in the same configuration as the initial configuration, right? I'm deliberately using the word configuration and not position, because see, it crosses in one cycle, it crosses this point twice. So not just repeat of position, but also the repeat of velocity. Okay, so so it is going to repeat its configuration after the LCM of the x time period and the z oscillation time period. Okay, now let's look at the maths of it. So since the sum of distance of the bead from two pegs is constant, if it were to move in the xy plane only, its locus would be arc of an ellipse, as I told you, with pegs serving as the foci of the ellipse. Okay, and accordingly the distance between the pegs would be 2ae. So this is the standard property of ellipse. You must have studied in your chapter on conic section that a to b distance is 2ae, where e is the eccentricity of the ellipse. Okay, also the distance of the bead from the line joining the pegs a and b would be the semi minor axis, right? So this is your b, and from the focus to any point, the end points of minor axis, the distance is a. That's also standard property of ellipse. You must have studied in the conic section. So this distance is a is the semi major axis, this is the semi major axis, and this is b. Of course it's going to oscillate like this and going into the page and out of the page. Okay, so also the distance of the bead from the line joining the pegs a and b would be b, where b is the semi minor axis of the ellipse. Okay, if r be the radius of curvature of the ellipse at the bottommost point, then the time period for the oscillation in the xy plane is simply 2 pi under root r by g. See, if there is a pendulum which is going in a radius r, then what is the time period? So you know that for standard pendulum that the time period is 2 pi root l by g. And from the energy point of view, it doesn't matter whether you are going in a vessel or some cylinder of radius r, or you are tied to a string. It's one and the same thing from the energy point of view. So the time period, if it is oscillating in a vessel of radius of curvature r, then the time period is 2 pi under root r by g, right? So now if once I know the radius of curvature of the ellipse, I will be able to find out the time period in the x direction. So what's the, let's say the equation of the ellipse is x square by a square plus y square by b square equal to 1. That's the standard equation of the ellipse. Now the radius of curvature of any curve is given by, this is the standard radius of curvature formula. You might have studied it in your basic mathematics, or maybe somewhere in your mathematics when you were doing calculus. Even if you have not studied, you can memorize this formula. It's a useful formula in some of the problems. So radius of curvature is 1 plus y dash square whole to the power 3 by 2 divided by y double dash. So but at the peak or valley, you know that y dash is 0. Whenever the curve has got a peak or a valley, the first derivative is 0. So then this formula simplifies to r is equal to 1 upon y double dash. So if you find this formula too complicated, at least you can remember this formula, because many times we are only interested in radius of curvature at the peaks and the valleys. Okay, so I have this equation 2 and I want to find out the radius of curvature. So I differentiate it with respect to x. So what do I get? So derivative of this is 1 by a square is constant, and x square derivative is 2x, plus 1 by b square, and the derivative of y square is 2y into y dash, right? 2y into dy by dx. We are using the chain rule. So this must be equal to 0, derivative of 1. Okay, and what is this point at which we are wanting the radius of curvature? The coordinates of this point are 0 comma minus b. Okay, so now I can differentiate this equation once more, and what do I get? So with respect to x, this becomes 2 by a square, because derivative of x is 1, and then this 2 is a constant, I take it outside, b square, then y dash derivative will be y double dash plus y dash squared. Okay, and this should also be equal to 0, and I know that at the valley this y dash goes to 0 and y is your minus b. So I just put y as minus b and y dash as 0 and rearrange this equation to get the value of y double dash. So when you calculate y double dash, you can do it mentally also. If you just rearrange this equation putting this as 0 and this as minus b, you will get y double dash as b upon a square. Okay. So therefore radius of curvature simply becomes a square divided by b, where a is the semi-major axis and b is the semi-minor axis. Okay. Now I can use this in equation 1. What is the equation 1? Tx is 2 pi under root r by g. So that becomes 2 pi under root a square by bg. Okay. So this was our time period for oscillation in the x direction. Now for oscillations in the yz plane. So in the yz plane, that is into the page and out of the page, the oscillations going with AB as the instantaneous axis. So this type of oscillations we are considering now. AB serves as instantaneous axis of rotation with radius of rotation being b. Okay, if it were given a kick in the z direction alone. Okay, so yz oscillations, the time period is like that of a simple pendulum of length b, and that is simply tz is equal to 2 pi under root b by g. Okay. Now overall motion of the pendulum is superposition of oscillations in the yz plane and in the xy plane, right? Yz plane and the xy plane. Okay, so we are going to superpose. So if the time periods in these two directions bear a rational number ratio, the motion is bound to be periodic with a time period which is the LCM of the two time periods. So you must be knowing that whenever we have two rational numbers, we can always find some LCM, although that's not true for any two arbitrary real numbers. But if there are rational numbers, definitely there will be some LCM and there will be some closed path formed if the two time periods bear a rational ratio. Okay, so motion is bound to be periodic with time period which is the LCM of the two time periods. The path traced in such an oscillation is known as a Lisages figure. So Lisages was the name of the mathematician or physicist probably who studied these types of curves and developed some theory about them. So now we are given the Lisages figure that our bead is making, and this is not to the scale obviously. The figure is much smaller. Actual figure, if we are giving small kicks, you know that the SHM works out nicely only for small oscillations in case of pendulums. For large amplitudes, the time period formula do not hold, so assume it to be a highly exaggerated figure. Okay, now in completing the full circuit, when we are going along the full circuit, see, if we talk about the positive x extreme, so how many times does the particle hit the positive x extreme? You can see this curve. If I draw a tangent at the positive x extreme, so here it hits the positive extreme, here it hits the positive extreme, and here it hits the positive x extreme. Starts from the mean position, hits the positive x extreme position thrice, and then hits the negative x extreme position thrice, and then again comes back to the mean position. That means what? The time period, in the complete cycle, 3x time periods have completed, because we got 3 times the right extreme position, right? So that means what? And in every time period there will be once it will be visiting the right extreme position once. So that means what? 3, if we call tx as the time period in the x direction, so 3 tx have passed in the complete cycle. Okay, and similarly if we see the y direction, in y direction, if you see how many times, not y direction, this is supposed to be actually z direction, the top view. So if we consider the negative z direction, or you can say this side will be the positive z, I have messed up the direction, so it according to my original figure, this must have been positive, but doesn't make any difference to the analysis. So if we look at the z direction, so how many times does it reach any of the extremes? See, so it reaches the extreme once, twice, thrice, and 4 times. So in complete circuit, it reaches its any of the extreme positions 4 times. So that means what? In the complete circuit, 4 times the z time periods have completed. 4 if we call the time period in the z direction as tz, so 4 tz have completed in the complete circuit. Okay, so that's what I have written. We see that in completing the full circuit from O to O, the particle attains the right or left extreme position thrice. This is talking about the x direction, which means it has completed 3 cycles of oscillation in the x direction, and in the same time we see that particle achieves its z or minus z extreme position 4 times, which means it has completed 4 oscillations in the z direction. Its complete circuit from O to O. When I say complete circuit, means the entire path has to be traced, not just reaching for the first time, because there's a crossover here. so it will be crossing it once like this and another time like this. So so full circuit means it has traced the entire curve. Okay, so therefore we can say that 3 times Tx is equal to 4 times Tz. Okay, and from equation 7 and 8 we just substitute the value of Tx. So we got Tx as 2 pi under root a square by bg. So 3 into 2 pi under root a square by bg should be equal to 4 times 2 pi under root b by g. See, I'll just show you the equation 7 and 8 we had derived earlier. So this was your Tz based on this pendulum length, and then there was this equation 7 Tx based on this radius of curvature that we had found. The radius of curvature we had got here as a square by b, right? So we just substituted the values of Tx and Tz. Okay, so 3 into this is equal to 4 into this, right? So, and if you just rearrange this equation, cancel off a pi and 2 pi you cancel off square and rearrange the equation. So what you get? You will get b is equal to 3a by 8 just by rearranging this equation. And we also know that in any ellipse b is also equal to a into under root of 1 minus e square, where e is the eccentricity, and that will give us the value of e. If I just put 3a by 8 over here, so 3a by 8 is a into root of 1 minus e square. So we can just solve this for e. You solve, the e comes out to be root 55 by 8. Okay, so once I have e, then I can readily get the value of L and D in terms of e. So this D is 2ae, so that will becomes root 55 by 4 times a, right? And L is obviously 2a, so D by L ratio we had to find out. So D by L comes out to be root 55 by 8. So that was the analysis of our mysterious pendulum, or probably we should call it the Lisages pendulum. And I hope you enjoyed this analysis and you enjoyed this challenge. And if you did like this challenge, to appreciate my effort, please do give it a thumbs up, and do recommend this video to as many friends as possible through various WhatsApp groups or Telegram groups or Discord servers or whatever media you might be using, social media. Or rather academic media I should call. JEE students don't have time for social media, right? So whatever academic media you use for collaborating with other students, or your whatever academic people you collaborate with, please do share my video. And if you have not subscribed to my channel, please do subscribe to my channel. My channel is not monetized. It's the love that I receive from you in form of subscriptions or comments or likes that keeps me going. Thank you very much for watching this video. Wish you a very happy festive season. Do keep coming back to my channel for more awesome